Welcome to part 1 of a lesson on understanding the gas law from the atomic level. What we mean by the gas law here is just PV equals nRT, which we've used in chemistry classes and have used a little bit maybe in physics already. But what we'd like to do is take our understanding of the kind of large-scale ideas, specifically the large-scale idea of pressure and temperature, things that you can measure with equipment that you have in the lab, and take it down to the atomic level and ask what each of these concepts mean when you're looking at individual atoms. And we'll try and use the same ideas that we've used previously in physics. And we'll go ahead and get started. We know that the basic idea of pressure is a force per unit area, but immediately we have to ask the question, what kind of force are we talking about if we take this down to the atomic level? One way of thinking about this is this: if we had a box, a certain volume, filled with gas molecules, we could say that we probably understand that the gas individual atoms are moving in all kinds of different random directions. And so what do we mean by the force associated with force per unit area for pressure? In this case, if we were to zoom in on one collision, what we'll look at is the left-hand wall. What we notice there is we'd have a gas molecule that is colliding with the wall. And just the use of the word collision suggests some work that we've already done in physics. Collisions are associated with impulse. So the first thing we'll do is we'll equate our idea of force on the microscopic level with the impulse of a collision between an individual atom and one of the walls. Now, from our previous definition, you know that the impulse is a force times a time, and that's equal to a change in momentum for the object. We can rewrite the change in momentum. In this case, the mass of the particle is not changing, so it's equal to the m mass times its change in velocity. Now, the force we're interested in is the force of the collision of the individual atom in the side of the wall. And so we can rewrite our little equation as the mass of the particle times its change in velocity divided by the delta t, where delta t here is the time it takes for the collision to happen. And that's kind of what we mean by the force on a microscopic level. Now, if we zoom in on the collision, we can say a little bit more about what's happening here. Well, we say that the atom is moving in with a particular velocity, hits the wall and bounces back. What we're going to assume is that this is an elastic collision, so the velocity on the way in, the speed I should say, is the same as the speed on the way out. Or now we can say something about the change in velocity. Since velocity has a direction, we do this change in anything as final minus initial. Final is to the right, so that's a positive velocity, minus a negative velocity on the way in. If those average velocities are the same, the total change in velocity is twice the original velocity. And now we can make a substitution into our equation on the right and kind of better define what the force of an individual collision is. We're not quite done because we want not the individual force of a collision, but the total net force of all of the collisions that are happening inside the box. That would give us the macro idea of pressure. And in this case right here, you'd see that that would be the force of an individual collision times the total number of collisions that take place. And rewriting what we have here, you can kind of see that all we've done is added the number of collisions, but with a little bit of trickery here, we can regroup this so that our time for each collision is paired with the number of collisions. And what that means is that's number of collisions per unit time, which is kind of the rate at which collisions are happening. Okay, so that's basically what we've done here is we've kind of figured out what that force in the force per unit area means on the microscopic level. And here's what it tells us about the microscopic idea of pressure. The microscopic idea of pressure must depend somewhat on the mass of the individual atom or molecule that's hitting the wall. It's going to depend partly on the velocity of that collision. And finally, it's going to depend on the rate at which those collisions are happening. And this little derivation that we've done here is taken us from, using regular physics idea, from the macroscopic world down to be able to say some things about what's happening on the microscopic level concerning this idea of pressure. Now, it turns out that further developing this equation that we have here will tell us something kind of surprising about the idea of temperature on the microscopic level. But that'll have to wait till part 2 of the lesson. Thanks for joining me.